Hi, David Vizard here, and you are watching PowerTec 10. So what was I doing in our opening shot? Well, I'm poking around inside this Profiler Sniper Junior manifold. It's a big block item, and I'm just collecting the data on the runners to go with the dyno testing we've done. Now I can tell you right now, save you all the anxiety of wondering what big block manifold to choose for a single 4-barrel dominator. This is the one you need, right? I'm going to be doing a video on it down the road, but anyway, that's not the subject of our talk here. So let me tell you what this is all about. Well, the subject material for today is, well, let me kind of bring it online with a little story here. The name Richard Holdner should be familiar to anyone that's a true hot rod enthusiast and likes to see the results of dyno testing. Richard's has been his MO for years, and he's been doing articles and videos that are pretty much dedicated to just saying what's the difference between this and this on the dyno, and he does an excellent job. One of the exceptions to the rule was he started a video and it was over several subjects, but it started off talking about the coefficient of discharge of an intake or exhaust port. Now, sometimes that's called just the discharge coefficient. Anyway, what he did in this story, and it's on YouTube, just put in Richard Holdner in the search engine and I'll find dozens of videos by him. He started off with a brief description of what the coefficient of discharge is, and so that kind of dialed the viewer into what he was talking about. But he had other things to talk about as well, and only took it down the road as far as the basics are concerned. And I thought, you know what, this subject here is the bottom line of a lot of what you can tell about a cylinder head, and it's the subject of great confusion amongst many hot rodders. So, thank you, Richard, for the inspiration there. What I'm going to do is take it from where you left off. So that's our subject. What is the most important number other than CFM, and it's about equally important, is the discharge coefficient of the port. Now that's a fancy way of saying it's flow efficiency. So let's get to it. We're going to really look into this in depth. I often tell people that the job of a porter is essentially to get air to go around corners that it really is not too keen on going around. The more skilled that porter may be at that, probably the more horsepower his cylinder heads will make. Now, granted, there's more to it than just that. But what we have to consider here is what are the limits of the flow that can be had through a essentially perfect port. Well, this weird looking device here is going to tell us what we need to know. Essentially, it's a straight port. In other words, it's got a 90-degree downdraft angle. The valve is down here. This essentially is the valve stem. This around here represents the combustion chamber in unshrouded form. Right, and what we're going to do is we're going to progressively open that valve and see what it will flow. How do we know how much it should flow if it was perfect? That's quite simple, but we'll get to that in a moment. Now, there are no restrictions to this other than the valve itself. The port is perfectly straight and streamlined in a Venturi-like manner, right? So we should get some pretty good flow numbers from it. Now what we need to do is to compare that with perfect. What's perfect? Well, that's quite easy to demonstrate here. The first move we should make here, I think, should be the definition of our units that we're going to use, so that those of you who are not too familiar with flow bench terms and techniques get brought into the picture. First, let's talk about the test pressure units that we're going to use. When I talk about test pressure, I mean either the pressure or the suction we use and apply to the port so that we have what we call a standard pressure drop. In other words, if we're going to suck on the port or blow on the port, depending whether it's intake or exhaust, we need, the convention rather, is that we have a certain test pressure. This test pressure, the most common one, is 28 inches. And that's a pressure brought about mostly by the influence of Smokey Unique. Many of you older hot rodders will surely recognize that name. Anyway, 28 inches, right? And you think, how's that a test pressure? Well, that's the water column, right? Imagine that you've got a long straw and you put it in a bath of water and you suck on that straw. When the column of water has risen to 28 inches up the straw from the surface of the water in the bath, that suction on that straw is then equal to a water column of 28 inches. That is a little over 1 psi. Anyway, let me show you the water column. It's actually an oil one for a flow bench so that it doesn't get all messed up over time. But let me show you on the flow bench where that column is. Here is the side of the flow bench. If you look to the right of the red oil column there, you'll see a scale. And as we go up, so it gets more and more until it tops out. It's something like 40 inches. As you most likely saw, the column we're talking of here is red, and it's actually oil, not water. Also, the graduations, the inch graduations on it, are actually bigger than a real inch. That's because oil is lighter, so the scale has to be bigger to compensate. But anyway, let's move on to the next topic here, which will be whatever constitutes a discharge coefficient of 1. That means that, in essence, whatever we're testing is 100% efficient. If the discharge coefficient was 0.9, then it would be 90% efficient. Now, how do we come about a number for the 100% efficient? Here, and I won't go into all the details of how that number was arrived at, but because I'm not here to teach you how to get into fluid dynamics, a university course. What I'm here to do is to tell you how we arrive at this number as it pertains to cylinder heads. Basically, we find that if we draw a pressure or vacuum of 28 inches of water, then the amount of airflow per square inch of the orifice being tested, or the test subject, it will pull through 146 CFM. That will represent a 100% efficient port. So that's our goal. So with the aid of the IOP program, I'm going to demonstrate just how we can see what a 100% flow efficient port is and compare it with what we actually get. So let's just check that out. Our straight port test piece has a 2.02 intake valve. The relevance of this is that this blue line here represents a lift of 0.25 D. That is 1/4 of 2.02. That comes to 505 thousandths. Now that is a critical number. The orifice size we measure as per SAE standards increases until the valve gets to 0.25 of its diameter in lift. At that point, all the orifice area that can be presented to the cylinder has been. So any lift further than that presents no more area. So if we have 100% flow, 100% flow efficiency, the curve looks like this. It's a straight line until 505 lift, that's 0.25D. If we had a 3-inch valve, we would be looking at 0.75D for this lift curve. But on our particular test one, it tops out at 505. And at that, since no more area is available, the flow should top out like this. So this is our 100% efficient curve. You'll see that that valve should flow approximately 468 CFM at 505. Bad news is that even with the straight port we have, it doesn't match that. So let's have a look and see where our straight port actually goes in terms of flow efficiency. On to our next graph. Here is our 100% efficient line. That's a discharge coefficient of 1. And here is what our straight port, as you just saw on the flow bench, delivers. You can see that what we could theoretically obtain and what we actually achieve are substantially different. Now then, that's our flow curves. So let's now look at our discharge coefficient curves. That is the efficiency with which our rig is utilizing the space that it has to flow through. Here we can see that we have a discharge coefficient of 1. Here is our actual discharge coefficient. Right, so you can see even with a straight port and a valve that is tulip shaped, this is typical of what we can expect. But that doesn't mean it can't be improved on. That is a basic parallel port. An airflow, the form it requires to make the best discharge coefficient, is never obvious, especially when we put a curve in the port as we need to for cylinder heads. If it was simple, we would not need a flow bench. So we can sum up our discussion on the coefficient of discharge by saying that essentially it's just a measure of the port's efficiency, or the port and valve entity's efficiency to flow air. It won't take much thinking to realize that the most influential aspect of a port and valve system is the valve itself. We can make the port any size that we wish, but we're restricted on the valve by how much room there is in the cylinder. So we could have a system which has a high discharge coefficient by virtue of a massive port feeding the valve that's limited in size by that bore. Let me make an example here. Imagine a bucket, you know, a big one, this diameter at the top and this diameter at the bottom, and in it, it's got at the bottom, it's got a valve 2 inches diameter. You can see, and let's say that valve is very streamlined into the seat and out of it, so it's as close to a perfect valve as can be had. So we now flow test that, and we'll find that it has a very high discharge coefficient. But would a port the shape of a bucket with a valve at the end of it actually make power? No. The port velocity is so slow that it has no ramming efficiency, and it will backflow very easy. Now, somebody said, no, it's been said by a lot of people, mostly people who have never designed a cylinder head or an engine, that the internal combustion is a simple air pump. No, it's not. If it was a simple air pump, we would have conquered all of its challenges that it presents us years ago. No, it's a very complex air pump, right? So the next time you hear that an engine's just a simple air pump, it's something of a cliche, and it's probably written by somebody who hasn't given this any thought further than what they've heard somebody else say. But let's get to the point here. We need to have a port that not only flows a lot of air, but also does it from the point of view of efficiency, not from the point of view of size. Now that excludes the valve, right? So when we cut ports in a cylinder head, we have to cut the port to a shape that flows efficiently due to, and not flows of those big numbers due to its size. So we should have learned two things here, right? We need airflow, and we need to generate that airflow efficiently. That is the crux of the matter. So that is our coefficient of discharge, how efficiently the port works. Is that everything we need to know about a port? No. And let me go into that now. So we know about CFM, and we know, if you've taken everything in here, roughly how important the coefficient of discharge is. But is that anywhere near the end of the line with understanding ports? Unfortunately, it's not even close. What I want you to do here is to make note of this section of this graph here, right? And I'll zoom in on it so that you can see it closely. If you look very carefully, you'll see the flow curve of our straight port actually exceeds the line of what is representing 100% efficiency. So how do we get that line there to be greater than 100% efficient? Now it's not showing it up very well here because of the scale of the graph, but what we can do is switch to the coefficient of discharge graph and see what the difference is. Here's our coefficient of discharge curve. This is our 100% efficient curve. As you see, it's a straight line. Here is the curve for our vertical port. Look at this. It's 112% efficient here. How did that come about? Let me explain. So how do we account for this 112% efficiency here? The answer is quite simple. Pressure recovery. Two words. But exactly what does that imply? Well, if we look at the seat design up close, we see that it actually resembles a venturi. And a venturi's principal characteristic is that as the velocity increases in the minor diameter of the venturi, so the pressure drops. That's how a carburetor works. But as it leaves there, it recovers that pressure as it slows up. So it converts velocity energy, kinetic energy, into pressure energy, or it converts it one way first and the other. And this is what's happening here. Now this is just one characteristic of an intake port or an exhaust port that is rarely talked about. You may find it in university books, but outside of that, not so. Now the thing is we can have this pressure recovery in a port in 1, 2, or 3 points in the valve lift, depending on how effectively we've designed our port. So I've covered the discharge coefficient here, but that is certainly not the end of the line. We have to deal with things like pressure recovery, we have to deal with velocity, kinetic energy, the kinetic energy density in the valve, just to name but a few. and wet flow and so on and so forth. So port design is not just a simple thing. That's where I mentioned whoever said an engine's a simple air pump is probably not educated very well on the subject of engines. But anyway, if you want to learn more, then we are getting into the realms of stuff that is much more for professionals here. So I suggest at this point you take a look at the 2 videos I've done on this port program. But before we go, let me just show you the difference between these 2 ports in terms of velocity, port energy, and port energy density. So here we go. There's port velocity. Not surprisingly, it looks exactly like the port CFM curve. But that's because of the situation involved. Now let's look at port energy. Right, you can see our port energy for our perfect valve is way higher than for our actual vertical port. So you can see we've got a long way to go to achieve parity with it. Now let's look at the port energy density. Right, again, it's a similar curve, but that's because of the way because of the test subject to our last graph. But we need to learn about that and what relevance that has. So 2 options you've got here that you can take up. First, check out my videos on the IOP program. Numbers going across the bottom of the graph, the screen. And if you want further information and you want to come to one of my cylinder head or engine building classes, then here's the contact for that. If you've enjoyed this video and it's taught you something, do us a favor here. Hit the like button and hit the subscribe button. The more people we have on this channel, the more in-depth I can do this material. Right? We're hoping to hit the 10,000 subscribers pretty soon. So please go for that subscribe button.